Yeah.
Okay.
So somebody else is
So
joining.
not the usual person, somebody else. Hello? Hello, can you hear us?
Hello, yes.
Hi.
Yeah, hi, Shamir.
Hi. So this is your first time or have you been here before?
Yeah, this is my first time.
Okay. So yeah, I mean, we've been doing this for a while. So basically we are currently analyzing this PV data, at least microgrid data from photovoltaics, and it's just basically data science. We're just they have already done some prediction. We are trying to do something and compare what we would get from them. So since you're joining first time, just like a quick thing is that there is no real agenda for these. So this is just one problem that we just picked out randomly. But how well versed are you with, in general, with data science and pandas?
Yes, yeah. So yeah, regarding Python, actually, I'm very new to Python. So I think should I refer to your old videos, then maybe join later?
I mean, you can always be here. That's okay. It's just like that's what I usually ask. That if you need help, you can of course look at the previous videos in the playlist.
Okay.
And other than that, there isn't not much. I think. Do you have the link to the playlist?
Sorry, can you repeat again?
No. Do you have the link to that YouTube channel playlist where I have these?
Yes, I can get it from YouTube.
Okay, fine. Yeah. So
I have seen the videos.
So I think those start with the basics of how to install some basics, Python, NumPy, pandas, everything. So yeah, I mean, you can get started with that.
Yeah, sure.
So and you might also find the general way of going about doing some data analysis. Even if you don't know Python very well, I think you can just see how things go. I mean, of course, if you have the time to do it, just how things go with the data. I will give a brief. I will just talk briefly about what we have done so far, and then and then it will be. We'll try to do something. We still don't know exactly what we want to try. We had some discussions last time, but we will just look at the data and see what we can do about it.
So Harish is here. Hi again.
Hi Harish. Okay. Harish, you have anything to ask, or we can start with whatever status?
We can start.
Okay. So I'll just quickly recap what we were doing, and then I have shared the screen. So you see the screen?
Yeah.
Okay. So what we decided to do was there is a data set in Kaggle, which contains the data set from microgrid in the Belgian city of Liège, and so we wanted to see what we can do with that data set, because I was interested in doing some analysis of energy and microgrid related data. So there are three different aspects of this data set. We have a climate model weather forecast, which is a 15 minutes resolution. Then you have PV monitoring and consumption. So real data from the microgrid on how much of PV solar panel generation of power is happening and how much is the microgrid consuming. And this is for a resolution of 5 seconds. And then there was a forecast generated by some recursive neural networks and another model for the same PV production and the load consumption, which was at 15 minutes. So this is the data that we have, and what they have done is, using this climate model weather forecast, they have generated along with some past history. So we don't know what, I haven't really read exactly what past history they have used to create this forecast. So the idea, however, is that the forecast and the real data have been given for the same period, around the same period, so that we can compare how well they do and where is it's not doing well. So I sent a version of this Python Jupyter Notebook file into the Google groups a couple of weeks back. Perhaps after this session, I will send the new one as well to see if people want to see what has been happening. You can check that. So we kind of wrote down a few tasks that we can do. So one was to prepare the data such that it is synchronous with time, because there was data not available all the time for all of them. So we picked this date as between 20th May and 17th June as the date. So what we have done is to synchronize two of the data sets. So I'll show that. Then reconciling the sampling rate, like there are some which is in 15 minutes and some in 5 seconds. So how do we manage it? So these two things we kind of have done for two data sets. So, and then the rest we can probably think of what. So what we have done so far, I can show you. So before going for it, we saw that all of these are in different CSV files. So we handled those CSV files, then put them in a way so that we can read using PD here is pandas. Using the read CSV in pandas, we could read actually each of the files into a data frame. And then what we did was we also created a datetime column using the data that was available for date time. So in fact, the date time was not in datetime format. So date and time was in a string format. So we converted and then created a datetime format and all that. So this was the pre-treatment that we have done. I'll probably see if I can add a few comments before I send across this Python notebook, Jupyter notebook. And so then what we did was we focused on the cutoff dates and ensured that the data that we were interested in will be only within that date. So what were the data we were interested in? This is the photovoltaic generation that has happened over that 2 months period, and the weather over the 2 months period. So since the photovoltaic generation is at every 5 seconds, so we also did use the resample approach of resample method of the data frame to, and then in fact we did a sum. We did a sum, and we have a new data set which contains only once in every 15 minutes instead of once in every 5 seconds. And then what we did was we put them all together. So we have PV and all the weather related things in one data set. So we started then to analyze which one are meaningful. So we have several parameters like low clouds, medium clouds, high clouds, precipitation, relative humidity, snow, surface temperature. All of these weather factors are going to be responsible for how the PV generation happens. And so we were trying to look at how are they affecting. So this is where we were, in fact. We can see that we also tried to do categorizing the weather data, the cloud data, in fact. So it looks like this low clouds, medium clouds, and high clouds refer to at what height these clouds are. We thought we'll just need one type of clouds. So essentially we said, okay, clouds are going to affect how much solar power is going to come and hit the PV. And so we'll put them all together in one of them. So we took a maximum value of those clouds, and then we created a new column called cloud cover. So we essentially have a cloud cover of this form. So you can see here CD, CM, CU are the cloud different cloud levels, and the maximum is what is our approach, which is the red. So it essentially says that it's quite cloudy most of the time in Liège, which is not surprising in Belgium, especially during the springtime. Yeah. So, and then we were trying to do some categorization. So we did a categorization once of the clouds. So we have 4 categories now of the cloud cover in category form. And this is what we have so far. You have a cloud cover category, which has 3 for if it is, I think it's between 1, 0, 1, 0. Okay, I think I have to change this. This one is 1. Okay, 0, 1, 2, 3. We'll do this, and this should be okay. So 0, 1, 2, 3 are the cloud cover values, and then we are trying to understand what to do with them. So we have these values, and so we were now trying to understand what are the factors that we can take up and see what is there. So okay. So Shiva, we can start probably with
so if you look at that last data frame,
so
for example,
this one,
so here we have actually only taken those columns that we think are relevant, right? And we have except I think we have a couple of columns which are addition, and we have the first column which is PV, right? So now the PV column is it the actual PV or is it a forecasted PV?
This is the actual PV.
Actual PV. So what we can try to do, I think they have already done a forecast, but that forecast is based on neural networks, recursive neural networks. So now recursive neural networks is actually a very rigorous process, because if you know what a neural network is, basically a neural network is like this entire layer of neurons. So it's basically a huge, you can say, matrix of multipliers which are all connected together, right? Imagine it that way. So you have layers and layers of multipliers connected together. So you have the input coming in at one end, and all these inputs are being multiplied by several factors, going to the next level, again being multiplied by factors. So they are multiplied and summed together. That's what happens. So eventually when you get the output, you have the entire process where these inputs have been multiplied, summed together, added together, and all those things. So that's what it is. Now recursive, the main challenge in recursive neural networks is you need to determine what should be the product so as to achieve the output and input, right? So initially you would want to train it. So the way to train it is you take known input, known output, and you calculate all your factors with that in mind. That's usually the training method. Now recursive neural networks means the method goes back and forth. So you start from the input, go to the output, go back to the input. It's a back and forth method, which is why it's fairly rigorous, and the result is it's one of the most accurate methods around. I wouldn't say the most, maybe there are more accurate methods, but it is one of the best ones. So what we can try to do is we can try to play around with some other, other techniques, and see how they rank up to recursive neural networks. They will not usually, but still it would be interesting to see how that happens. So the first question is, can you find out where the forecasted PV is?
Yeah.
Actually, before that, let us clean this up, because we already have, if you look, we already have generated the last one, which is cloud cover category.
Yeah.
So we can
remove.
Exactly. We can remove CD, CM, CU, and I think we can even remove cloud cover.
Yeah. So it will be.
Actually, it is drop. So if you look. Look, it's DFP weather drop, and you can just you have to open its this thing function method.
Function.
So you can do shift tab. So you see here you can specify labels, if you don't specify anything, like, you know, if you just go up a little, if you scroll up, you see these are your parameters. So you can specify the index specifically, or you can specify the columns. Okay, and here again there is in place is equal to false is the default. So if you just specify the columns, it will return back another data frame without changing it. So we have to specify in place is equal to true if we want, but of course we can first verify. So what I would say is here we just say columns is equal to, and then in a list we pass all that we want to drop.
Okay. So I will just quickly check the names. I mean, what are these? So clouds. After that, I think we need precipitation, perhaps, and maybe we don't need relative humidity.
Yeah.
And because it is during the May period, I don't think we need snow height.
Yep.
And surface temperature is required. Horizontal radiance, yes. Solar irradiance, yeah. Yes, perhaps. And then temperature. And then wind speed, I think it's also not
wind
required.
Speed we can drop, so yes.
Both wind speed we can drop. So, okay. So we'll go and drop them. I'll just check. Okay. So this will be a drop, and this is column, right? Columns equal to, and then we'll say CM, CT, CB, CU. Then we said relative humidity is not required. Then snow is not required. Then surface temperature is required.
Yes.
On wind speed 100 meters is not required. Then wind speed at 10 meters is also not required.
And you can
we can also remove the cloud count.
Exactly. That was something we did for the interim.
So we'll just check. I mean, I will now not do an in place now. So we just now have these.
Yeah.
Okay. So this is just what I think. I'll probably keep it in add it into another file, because we will then add the PV prediction, etc. into it.
Yeah.
Because I think they would have used, my guess is that we can only do a comparison, because the neural network, they wouldn't have used only these 2 months of data to generate the prediction. So they would have definitely used a lot more data, and my guess is, I mean, I don't remember if I had read the details, but I don't think anybody is going to train a neural network with 2 months of data to do a prediction on the same 2 months. So, I mean, if they did that, it's pretty suspicious of what they did.
Okay. Yeah, I guess that's okay. Anyway, like I said, we will probably not be able to generate any serious results, because we cannot go to something like neural networks. Those are fairly complex methods, for which you need a fairly rigorous mathematical background. So what we will do instead, we'll play around with some of the easier to use machine learning algorithms with Scikit-Learn. That's what we'll do.
Yeah. I think, and we will perhaps stick to these variables.
Yeah.
We don't have to go to other variables, because it's easier. 5 variables, 6 variables, it's okay. Easier. And then I'll just quickly check what are the other. Do you know if there are any something like in MATLAB you have this WHOS? What are the variables that are there? Do you have something like that in Jupyter Notebook to check what variables are there?
No, I don't actually.
Yeah, I'll check. So
yeah.
Oops. What is it? Heck, wait. How to check? Okay, sorry. Okay, variable explorer. Okay, there's something called the variable explorer. Oh God. Okay. Okay, it's
Yeah,
you have to
it's
make your own.
complicated.
So
Yeah,
I think we
okay.
will not do that. I mean, I just wanted to.
I think if you scroll up, that must be there. Yeah, PV.
Yeah. I know. I just wanted to see. I think this one has all of them. So it has. So I will just check because it contains.
I think it's
different
.keys. If you do keys, .keys. It's a method actually.
Yeah. So yeah. So within this you have. You have PV 15 minutes forecast for RNN. That's the thing that we need.
Okay.
So we just.
You can start a new column because cell. We can keep this.
Yeah, but I think there is another problem because there's some form of a look ahead prediction, I think. So it will not be a single column if I'm not wrong. So I'll just check.
No, what I'm saying is you can leave this cell so that we don't lose it. We can start a new cell.
Yeah. Oh, okay. Sure. Okay, we'll go down and then see. I will just check if we already put them in a different file because we did something. Okay, it is there in df all data. Yeah, after that we focused on a specific set of them. Okay, so df all data, and then we'll have to see pv 15-minute forecast from this. So you see that there are multiple columns. I think there's sort of a 1 day look ahead prediction.
I see.
So the 0 I think is for the current prediction, and then you have 96 is for some sort of a look ahead prediction. Maybe perhaps we should just take the single 0th prediction if I'm not wrong. I will just quickly see.
Maybe you can just plot these two.
Yeah. I'll just show you what they explain. Just trying to see if they have done that. Yeah. So the weather-based forecasts are multiple output with a horizon of 24 hours ahead and a resolution of 15 minutes. So they are quarterly produced on a rolling basis with a learning set of 1 week. So every 6 hours the model is refreshed and learning set is moved consequently. So yeah, I think we'll probably we'll plot it and see, but I think we will just have to use one point instead of all that. Okay. So do you want to put them into the same range of data like we did for the rest of them, because this we'll probably have to restrict the range.
Actually, you know what I would do? I would just plot that 0th column and compare it with what we're getting above. Okay, because just a quick comparison. That's it.
Okay, so this will be 0, something like this, right?
Yeah.
Okay.
Okay.
So I'll just try to make it a bit bigger and all that. And maybe we'll try to restrict it. I'm not really sure. Maybe I'm okay. And maybe I will restrict it to a shorter period.
Yeah. So like just make it like 1000 to, if you do the XLIM, if you just zoom down a little.
Yeah.
I mean, just scroll down. So like if you do, let's say 1000 to 1100.
Yeah, it's like 96 per day. So I'll try to, because 1000 is in the middle of the day. So I'll try to make it for 2 days and see at least 1 day pattern.
Exactly.
Yeah. So, and here, so we'll do an XLIM, is it?
Yep, excellent. I mean, really we should do the same rigorous thing, but this is like, we just want to like see what we have, what it looks like.
I will say 950 and 1001. So yeah, just something like this.
So it does look like it is over 1 day, right? It does look like it does look like the PV of 1 day. So if you compare these two mounts.
Yeah. I will just now see it's 1075 to 1130. I will put it that.
Now the only thing I'm thinking, if you just scroll up, finish there.
Just a second. One second. 160. Okay. Yeah. So yeah, go on.
So if you go up, like for example, here you see the scale is 0 to 100.
Yeah.
And if you go down, the scale is 0 to 1.
1. Yeah. They probably have to do something about it. And yeah.
So what have they done? I'm just thinking.
Yeah, I have no idea what is the scale.
Okay. You know what I would suggest then? Let us use the PV of the first one itself. That is just not the forecast data, because I don't really understand what forecast they've done. What we can do, we can use the actual measured PV and try to sort of predict what the PV would be using the weather data.
Yeah.
Okay. So that is our thing.
I mean, we are just doing an exercise, so we'll do a training data and test data to be the same. So
exactly. No, I mean, the training and test we can always split. That's not a problem. What I'm trying to say is that we just have to sort of look at the idea is to start looking at how we might be able to use the scikit methods.
Yeah.
Okay.
So,
just then, we've been talking for a while. Does anyone have anything to say or any comments or anything?
Questions?
Yeah. Okay.
Not from myself.
Okay, cool. Okay, so what I would say is let's Google Scikit-Learn. That is sklearn. So if you just go to open a Google page.
Okay.
So this is one of the popular machine learning packages, Scikit-Learn. There are others, like there is PyTorch. Besides PyTorch, which others are there? PyTorch and
there is something called stats model, right?
There might be. There are even Google has come up with something very recently, which I heard about. Apparently, it has even some other stuff.
There is stats model and there is Scikit-Learn. But does PyTorch have all of the necessary all of the
Actually, I have never used PyTorch. I have only used Scikit-Learn to some extent.
Yeah. I mean, I tried to use it, not yet. I have not yet used it as well. But yeah, Scikit-Learn is quite popular.
Mm-hmm. Yeah. Okay. So basically, what we are going to do in this beginning is in our case, we have quantitative data. So what we are trying to do is we have a certain number of inputs. We have a target output. We want to be able to predict this output using the inputs, right? Now again, disclaimer, we will not be able to achieve anything close to what you see in the graph here, right? That's not going to happen because we don't have much data. And also PV data is notoriously hard to predict. You need something like recursive neural networks and something like that. But what we usually do when you have quantitative data, that is you have a quantitative output and you have quantitative input, one of the most common things to do is what is called regression. Okay, so if you click on regression, so this is actually very nice read. If you're ever interested in this entire thing about what works, there are actually some very interesting documents here. It may be a little tough to read if you're first getting into it, but it's still, I would say, quite good documentation, right? So now there are several methods you will see, as you can see here, there are several methods. Most of them are linear models. So when you talk about linear models, it basically means that they're trying to do a line fitting. So like for example, the simplest equation of a line you can say is y is equal to mx plus c, right? So you remember how when we used to do basic practicals, right, like physics practicals and things like that, we had to plot. So we usually would plot, like when you measure something like pressure and temperature and things like that, we would plot a straight line which would pass through as many points as possible, or try to sort of pass through them if almost none of them fit, right? So that was a crude way of doing what is called as line fitting, because we are like kind of trying to say that there were experimental errors, but if this is the line that kind of passes through all of them, right? So what we are going to do is something very similar. So if you go to 1.1.12, you see generalized linear regression in linear models. So this is what we are trying to do. So essentially what we try to do is we are going to say that if we were to fit a line between the output and the inputs. So let's say for example here we have, let's say 4 inputs. So it's x1, x2, x3, x4, and you say y is equal to some intercept c plus a1 x1 plus a2 x2 plus a3 x3 plus a4 x4. Now you want to find out the intercept c and you want to find out the 4 coordinates. That is what you want to do. Now in order to achieve that, what they usually do is some form of optimization problem, like it's a minimization problem, and you can read it. So this is actually reasonably interesting read. I know another book which I cannot remember right now, but I will sort of send it out to you on the Google group or something. That is actually a very good read on, and it's a free book, so you can actually download it, but it's a free book. It's a good read on basic linear regression and basic other methods. So if you scroll down, what we need to do is to find out the y-intercept and find out all the different coefficients, right? Now you can read this if you want, but what we need is something like this, right? We need, here of course there is a 2D regressor, but what we need is like a linear model, right? From the linear model you can get linear regression. There is something called linear regression and we can use that, right? So I mean, like, just a question here again, I've been talking for a while. Does anyone have any doubts? So since there are none, I'll just talk about the basic idea of how we go about. Now first thing is we have an input and an output, right? Now first thing you want to do when you have an input and an output is you want to split it up into a test and a train set. So for example, what that means is you are taking your data set and you're splitting it into 2 types. It's like control and experiment, right? You are going to leave one as it is and you are going to train your model on the other data. That is your training data, right? Now using that you build your model. Now this model that you built, you're now going to test it on the other data which you had not used at all. That is your test data, right? So this is the idea. The idea is because if you test it on the data that you use for training, you will always get low errors. The real test of your model is when you test it on the data which you did not use for training, right? So therefore we need to perform 2 steps. One is we need to split our data set into 2 parts, that is test and train. And the other part is then we are now going to use the linear regression to create a fit between the input and the output. Alright. So here what I would say is you can just go and Google linear regression Scikit-Learn.
Yeah, okay, just a second. Yeah, so you want to go to the Scikit-Learn module?
Yeah, linear regression. You can even check out, you can even open that this thing, tutorials, but this is also fine. Somebody has messaged something. What is the no? Okay, anyway.
Sorry?
I see a no in the chat, but anyway.
Yeah. You asked some
okay.
doubts.
Okay, fine.
When you said, when you were asking for any doubts at that time, he sent a message saying no.
Okay, fine. Okay. So you see, this is how we are going to use it. So basically there is the linear model as Scikit-Learn. There are also other models, but the simplest is the linear model. Now, when you use linear regression, you are now creating a linear regression object, right? Now, these are the default parameters. See, fit intercept is equal to true, and that is you do want it because the intercept is the y-intercept. So if you look here, whether to calculate the intercept for this model, if you set no, then it will assume that it passes through 0, right? That is y is equal to mx plus c. You are saying it is y is equal to mx. There is no y-intercept, right? Now, this is not a good idea unless you know for sure that if all inputs are 0, your output is 0, right? But usually we do not know that. So it is usually a good idea to set fit intercept is equal to true, right? Now, the second one is normalized, right? That is, if you want to normalize it, then it will do like a kind of it will kind of normalize your data. But here again, you don't want to normalize because you are actually dealing with real data. Your PV is in actual numbers and your weather data is also in actual numbers. If all your data were in percentages, that is between 0 and 1 or something like that, then you can use this normalize method, right? Now, the next one is again copyx and n jobs. This is not, I don't really know what these are for. There's for other methods, I have not used them so far, but this is how we're going to do, right? So when you create one, you create a linear regression model. So the next thing which I would like you to Google is test train split in Scikit-Learn. Actually, you can open another window because you can leave this.
Yeah. This is a different one. This one is the
Oh, I see.
Right.
Okay, so now you can take your data, okay, and split it on your own. So for example, let's say you have 10,000 rows, right, data. You can say I want to use 3,000 rows for testing, 7,000 rows for training. You can say that, right? Now, the problem with you choosing it on your own is that there can be separate biases. For example, let's say that we are choosing data it could be that we are choosing data for training which has a lot of error, or we could be choosing data for training which has very little error. When you choose on your own something like that, you could be introducing human bias into your model, right? Now, the test train split will randomly pick out rows from your data. That is the advantage. So therefore, this eliminates the potential bias, human bias, that can be in your machine learning model. So that way, if you pick out random data and you try to train it on that, the chances are that your model is going to be kind of independent of any human errors that could have crept in. Okay. So what I would say is, let us look at this test train split, because this is the first thing which you usually do. You take your data, you split it up, right? So if you look at the thing, what it says is it splits arrays or matrices into random train and test splits. So first is you say the test size. Now you can specify a proportion, right? Now it usually says the train size is set to 0.25, right? Now we will look into that very soon. So for example, test size, train size, and then there is the random state, right? There is the random state, or there is what you call shuffling of the data. Here, this is if you are doing a lot of machine learning together and you want to make them all compatible, right? Let's say, for example, I was doing a machine learning model on several data simultaneously, and I want to ensure that all my test training are consistent. That is, every extraction is consistent among all the models. Then you would specify a random state, because then what happens? All the test train splits will be consistent. Now, in our case, it's only one, so it doesn't really matter, right? So now you can specify the shuffle. I would suggest always specify the shuffle, that is, let the default is equal to true be there, because when you shuffle again, when you feed in shuffled data to your machine learning model, the chances are that your machine learning model will be more rigorous in the long term, because then any data, for example, your PV is increasing gradually, reaches a peak, decreases gradually. Now we all know that when any quantity its value is large, at this absolute value is large, the errors in the measurement are low, right? At least the percentage errors. On the other hand, when it is early morning and the PV is just picking up, the error in the measurement may be considerably higher. So now if you do not shuffle your data, the chances are that the errors in your measurement could affect your overall model. So it is usually good to let it shuffle, and that is the default. Default is equal to true. So we just leave it as it is, right? So now what it returns is, it returns us a list, that is, it returns two arrays. Okay, it returns an array of test and train. So for example, if you go down, you check out the examples. If you scroll down, so you see now here what happens is we are taking you see an A range 10 and reshape 5 and 2. Just in case you don't know, what happens is you're taking a NumPy array of 10 elements and you're converting that into 5 rows and 2 columns, right? Now you are now, and then there is an output which is 5. So x is equal to, you see, 5 rows, 2 columns, and y is just 5, right? So when you specify this like this, x train, x test, y train, y test, this is the way to specify. So your first is what is your x, second is what is your y, and always train comes first, test comes second. Okay, then when you specify it like this, you see, specify x, you specify y, you specify your test size or your train size, either one, and you can specify a random state, or you don't have to. Now what this means is the test size is equal to 0.33 means that only 33% of your data will be used for testing. The rest will be used for training. And you see that is the case. Your training set is 3 elements and your testing set is 2 elements, because it is used that ratio approximately. It's very small data, so you can't really see exactly what's happening, but this is how you're splitting it. Okay. Now again, you see here, x train, y train, x test, y test, you see they are shuffled. The reason is because the shuffle was not specified. So shuffle, if it is not specified, it is by default true, and your data is specified, is shuffled. In the next case, you see shuffle is false. So you see the data is kept in the same order. Alright. So once again, I've been talking for a while, so anyone has any doubt?
Yeah. So this fit intercept, I got confused that like if it is true by default, that means like it has to go through the origin, right? You are saying that intercept is 0 in that case.
Yeah. No, if you say fit intercept is equal to false, because if you look, the default is true. So if you leave the default as it is, that is fit intercept is equal to true, then what will happen is it will try to find a y-intercept. If you say fit intercept is equal to false, then it will not try to find a y-intercept, because it says it is assuming that when our inputs are 0, your y is 0, and when your y is also 0.
Okay, true means it is finding the intercept.
Yeah.
By itself.
Yeah. See, for example, I'll give you an example. Like in our case, we have your temperature is not 0, right? Your precipitation is not 0, and there may be other factors which are not 0. But your PV is 0, right? So your inputs are 0, inputs are non-zero, but your PV output is 0. Now, when that happens, you do not know, and also vice versa. For example, it may so happen that your temperature is 0, right? But if your temperature is 0, input is 0, it does not guarantee that 0 degrees Celsius, it does not guarantee that your PV output will be 0. So therefore, there is a possibility that there is a y-intercept. And usually there is always the case that there might be a y-intercept. You should not assume unless you know for sure that if your inputs are 0, your output is also 0. So then in that case, you can specify.
Okay. So that computational complexity can reduce.
Exactly.
Yeah.
So it's like this. Yeah. It is like this. It's usually like this, that every machine learning model, if you use it as it is, then in that case, the machine learning model will try to adapt with respect to inputs and outputs and create a model. But if you as an engineer has your own domain knowledge, and if you apply that, that always helps in improving your machine learning model.
So this split thing also, so you're saying that shuffle. So it is shuffle. I not remember the format.
Yeah, I mean test train split, you see the last one is shuffle is equal to false. If you don't specify shuffle, it means it is true. Default is true.
Yeah. So suppose in some cases, so now we are taking the PV value in a day. So if we shuffle, the time will also shuffle, right?
No, it's like this. Yeah, no, that is the most important thing. When you use it, right, you must always specify it in this way: X train, X test, Y train, Y test. So it will always match your X train and your Y train. So it will never happen that it will shuffle them with wrong order. So for example, it may happen that it will move all the rows randomly, but the PV output for a particular sample will always correspond to the inputs at that time.
Okay. So now X is the first column and Y is the second column, right?
Yeah.
So if 5 shifted, that means like automatically 4 will shift.
Yes.
That particular cell will be shifted in between the different cells.
Yeah. Only most important thing you must remember, the order in which it is to specify. Like here, X train, X test, Y train, Y test. Always X comes first, then Y, and within X first train and then test, within Y train and then test.
Okay. Suppose in case if we want to split shuffle according to our wish, I mean that so suppose 1000 data is there, in that even columns will be at one point, like even numbers will be in the test data, and the odd values will be in the train data. So is there any issue will come with this kind of conditions?
I don't think so. You can do that.
We are shuffling, and maybe the computation will come down. I felt that, I don't know whether it will come down or
not. Again, it's tough to say. That is like hardcore mathematics. I don't know if it will actually decrease or not, because it has to do, usually, like I said, linear regression is basically a least squares fitting method, right? So again, you are like using an optimization method with respect to reducing the least square of error between the input and the output, the fitting. That's how it usually works. So would it help if it remains in order or it doesn't? I'm not totally sure.
Just one possible case where it will be useful to have it in order is perhaps in something like ours, where, for instance, if there is a temporal data, I mean, this is something I'm guessing. If there is a temporal data, it's better to have them split in some order, because if you randomly pick, and then if it picks too much on a particular time of the day for the training data, and then it gives you, for the test data, it gives another time of the day, then it's going to be predicting it quite wrongly. it. Because so I think in that case, for instance, I say that I need the training data to be from, let's say, the starting until 2/3 of the data, and the test data should be the last 1/3 of the data. So, or you can move around this 1/3 with a bunch. Like you always say that, okay, I'll split the data into 1/3, or 1/4, several 1/4 of data, and then I will choose the test data to be 1/4 in any of those different parts. So I think that will be important, because if we don't maintain the order, we may not necessarily be consistent with whatever data we have. This is what I feel based on what I see with ours. Did I make sense?
No, I think, see, the reason why, okay, now there's two takes on it. When that really makes a difference as to the time, right, or rather the order, when that really makes a difference is when each sample is affected by the past sample. So for example, if you have, let's say, a chemical reaction, right, let's say you're trying to predict nuclear reaction or the power of a nuclear something. Now, in that case, you are dealing with a reaction which is potentially a chain reaction, right? So, for example, something at a current instant depends upon what happened at the previous sample, right? And that sample in turn depends on the previous sample. In that case, the order would be very important, right? Whereas in our case, even though it's temporal data, the time at any point of time, if the PV, the energy it is produced, depends upon, well, it would of course have some impact, because there is nothing which does not have some kind of hysteresis. But even the PV, the amount of energy that the PV is generating, depends upon the atmospheric conditions at that particular point of time. The effect of the previous instant will not be that much.
Yeah, I don't think this is a dynamic system.
Exactly. Exactly. So that's why. But we can try both and see what we get. That's just no hurry, no harm.
Yeah, definitely.
Good. Okay, so I don't know if we have much time, but I think we had a long discussion. I think we can just have a little more Q&A before, rather than start coding. So feel free to ask, because we have 5 more minutes. I don't think we can do much today.
Yeah.
Hello?
Hello?
Hi, yeah, we lost you for a while, okay.
So, how to identify whether it is superficial or unsuperficial?
I didn't get you. What do you mean? Unsuperficial?
I think he said supervised or unsupervised.
Oh, okay. So it is like this. See, supervised learning is like this. When you have like in our case, you have some output that you have measured. Like we have measured PV data, right? So this is our output, right? For example, let's say you have some machine in your lab, and you have predicted the temperature rise in some particular part. Now you want to predict that temperature rise with respect to several other factors, right? Now in this case, you have identified a particular output, you have identified particular inputs, and you are now fitting your model with respect to such that the model gives you a particular output with respect to inputs, and you can compare. In such a case, it's usually called supervised. Why? Because you have an output in mind, you have certain inputs in mind, right? Now, unsupervised is when you have data and you might just be wanting to classify. So, for example, let's say you have collected data about machine failure. Okay, like so many machines have. This is all machines failed over, let's say 1 year. Let's say 10,000 data and different failure data. So now, for example, you may not be able to now say that there is some particular output and there is some particular input. You can say, okay, is the probability of the machine failing? That is one case. But let's say instead of doing that, you want to now say you want to classify your machine failure. Like for example, if you were to put all your machine failure into like a chart, can you see clusters? right? Like for example, some machines are failing because of lubricant. Some machines are failing because of ball bearing. Some machines are failing because of leakage. You are seeing these patterns. Now in this case, you do not have a specified input and output in mind, but you're looking for patterns in your data, right? So then this is called unsupervised machine learning. Does that make sense?
Yeah. So you're saying that we should have some clear idea about the output when we feed the data into the program.
Yes, again, like I said, in machine learning, these things are usually, like for example, even an unsupervised problem, you can convert it into a supervised problem if you say, for example, instead of doing clustering, you want to find out what is the probability of a machine failing, right? So you can convert that unsupervised learning machine learning problem into a supervised machine learning. Machine learning is fairly fluid. It is how you interpret it. There is no hard and fast that this is supervised, this is unsupervised.
Okay.
I maybe perhaps we can also say that at some point of time where we have data which tells us the relationship, like this is the input, this is the output, and we have the relationship. I mean, we don't have the relationship, but we know that given this input, this output comes. Unsupervised learning is typically the inputs are either too many or we don't really know which are the inputs and which are the outputs. And in such case, we can't really beforehand tell something about what is going to happen. And so we'll have to kind of like a baby, we just have to crawl around and discover things.
Yeah. Like I said, we are just looking for patterns in your data in unsupervised. You're looking for clusters, it's classification, clustering, grouping, that kind of thing.
Yeah.
So suppose computational geometry is there.
Mm-hmm.
So if we have the cloud data, like not cloud data, we call it as geometrical data as a point. So suppose if you want to identify a feature in it, so it will come to a unsupervised machine learning problem, right? So we don't know what kind of, suppose if we take a product, so we may have drilling ports, and we may have extrusions, we may have milling parts. So if you want to identify what kind of machine we use to get particular kind of structure in the product, then if you want to identify that, then it will be a unsupervised learning, because we don't know at what position, what kind of machine used to get that product.
Yeah, I guess so. That could be one way of looking at it. Yeah.
Because we don't know at what position, we even not saw that product. So it is identifying the features in it so that computer can understand it can do automatically the next time when the raw material goes into the machine.
Yeah, I guess that is one way of looking at it. Yeah.
Yeah, I think in some of these unsupervised learning mechanisms that they do, like I think these reinforcement learning does something like, okay, I don't know, you just give it the cost function, you don't tell us anything else. It goes and discovers what is there, how does the system behave by giving different inputs and outputs, and then you tell that, you give a cost function saying that you don't go outside this, you remain within a set or something like that, and then it discovers. So there is also another thing, like just supervised, unsupervised is not the only classification. We also have some other quite a different kind of way of doing things also. So I think these will depend on what exactly specific problem that we are dealing with, and then you can see it through either supervised, unsupervised, reinforcement, and I don't know if there are any other techniques as well these days. I mean, there probably are hybrids of these techniques that will exist.
Yeah, and then there's deep learning and things like that, where you're actually going into like layers and layers of neurons. So
yeah, it discovers features on its own, like it assigns features, and then it says, okay, this is a feature, and I'll use it. And essentially, it kind of becomes supervised for itself, but yeah, it's a bit weird. I mean, it is supervised, but it's also does a sort of unsupervised mechanism.
Why I asked this question is that in case of 3D printing, so there are so much complications in that we have to identify the features properly so that it can print a nice product. So if we won't identify an internal cavities, we can't even take the support structure. So in that case, if we feed the data and it gives the output that like this is the proper way of arranging the product, maybe this is the orientation in which we can, if we print the print the part, then we will get the proper output. So this is like huge problem in 3D printing.
I see. I don't really know much about it, so I think we'll have to talk more in detail because I don't know the process.
Yeah, I mean, I think the new usage of machine learning for these newer domains, like there is also in material science, people use it to discover new things. Sure. Sorry about that. So in machine learning, they use machine learning for what they call as new material discovery and all that. So in these kind of cases, what they do is they give a certain set of characteristics that they know that they are looking for, and so they give that as some constraints, and then the machine learning algorithm will try hundreds different types of combinations of materials and percentages and all that, and then we'll come up with some combinations which it finds it to be possible candidates for a particular application. So I'm guessing that in case of your 3D printing problem as well, you can do something like this. In the sense, you give certain set of constraints to the machine learning problem, and it will go around and check a few options, and then you probably will give you an idea of which are the possible candidates. It may not necessarily give you only one solution, because it depends on what kind of constraints that you put. But they do this nowadays. Like recently, they talked about how they used deep learning to essentially discover new materials quite fast. It was quite a difficult task in the past.
So can I know the difference between the reinforcement learning, machine learning, and deep learning, and deep reinforcement learning also is there? So these terms are not confusing, but feeling that like, is there any difference?
Yeah, no, when they say deep learning, it's about what type of new model they use. So whenever they say deep, that anywhere comes, it is about the use of neural networks that have multiple layers, multiple depth, or whatever, whichever they want to call it. So that is where deep comes from. So deep signifies model. And then you have techniques that you use with. So you can have supervised deep learning, where you use supervised machine learning methods, and then you have a deep learning model which you train with the supervised learning, or you have a deep learning model which you train using the reinforcement learning method. So this is what AlphaGo and I think it was AlphaZero, the Google's Go playing game, which essentially bet everybody those come from there. So then machine learning is just a general term for everything. But typically nowadays they have started to refer to machine learning only as supervised learning, which does not involve neural networks and all that. Some people do that, but I mean, I think that's just superfluous. Some people wanted to use it as a way to show off. But yeah, it's not. I don't think there is any big difference between. I mean, the difference comes from what do you refer to model and the learning techniques. Is it making a bit of sense, Harish?
Yeah. So, but whether it will change with the application also. Suppose if we want to take the feedback from real world equipment.
No, it doesn't. It doesn't matter. So this is referring to the techniques. Like it is saying that these are, if you want to look at it from what we already know, it's like math. So saying that, okay, maths has different ways, like you can model a system with differential equations, and then if you want to solve it, you probably have to solve it on a computer or with your hand. So you can solve it using an analytical equation. You try to solve it analytically, the differential equation, or you use a computer, convert it into a difference equation, use numerical methods and solve it. So these are ways to understand and analyze a differential equation. Similarly, you can say that these are different ways, given a system, given the set of data, these are different ways to look at the same thing. So which means it doesn't matter what type of model, what type of application you have, but it depends on what are your objectives, what are your features, what kind of data you have. So it only depends on, in the math analogy, it only depends on what differential equation you have. If you have a nonlinear equation, that's difficult. If you have a partial differential equations, that is even more difficult. So this only is about those aspects and not on where does this partial differential equation come from. It doesn't matter. If it is a partial differential equation, it is difficult. That's
Anyway, I think we're kind of overshot our time, so maybe we close this session. We can continue next time.
Yeah. Thank you.
All right.
Okay.
So, thank you so much. See you next week. Goodbye.
Yeah. Bye.
Bye-bye.
Bye.